welcome to this afternoon session. Our first speaker is Diane Fisher, and she will tell us something about how galaxies regulate their growth.
Yeah, thank you. So I'm going to be talking largely about feedback, which I think everybody in this room knows that is sort of quite a significant part of galaxy evolution. Basically, every single large-scale simulation cannot make any of the basic properties of a galaxy without incorporating feedback. You get the masses of galaxies wrong by factors of like 100 if you don't have some kind of feedback prescription, and things like the morphology and the sizes of galaxies is something that you need as well. But the problem comes in that once you step back, once you push past that statement, and you say, okay, well, how does feedback actually work, and how should we actually incorporate this? The consensus 100% breaks down, and nobody can agree on what the right feedback model is and how. And so we're going to look at kind of an observationally motivated testing of theories and see if we can maybe learn things that what does and doesn't work, and then how do they work when they do. We will talk about two sort of modes of feedback. The first is in a disk. This is a much more quiescent phase, and the arguments there are more about like does feedback, to what degree does feedback support things? We'll be talking about the sort of kiloparsec scale measurements, and then later on we'll talk about the more extreme things. There you have the M82 outflow, and we've seen this image in thumbnails about 20 times this morning, and it's just widely agreed that it is the feedback, it is this process of stellar evolution that is able to drive gas very far out of the galaxy, and that this is this critical process because in both cases, the main thing the feedback is doing to a disk galaxy is that it's essentially slowing down the star formation, and it's stopping things from going into runaway collapse. So first, as I said, we'll look at sort of the disk mode feedback. There's a whole lot of stuff on this slide, and it makes it look more complicated than it is. So inside of a disk, you have sort of a basic process of you have stars forming and exploding all the time, and they are generating an energy that we believe goes into the ISM. And that is used to address a sort of very basic observation of galaxies, and that is galaxies are not in runaway collapse. They are not all condensing at once. And so something is stopping that process, and it regulates the properties of the disk. From a radial point of view, we understand that this is essentially angular momentum. But vertically, every disk galaxy has a thickness, and so something is setting that thickness, and which means that something is pushing back against gravity. And then any theorist can come along and set a model for what that is, and you assume then that the system is in dynamical equilibrium. Eve Ostreicher did pioneering work where she sort of assumed that it was driven by feedback. If you make that assumption and then you say, well, at the sort of kiloparsec scale, the scale of a couple disk scale heights of a galaxy, the energy budget of feedback largely comes from your supernovas. So when you make those two assumptions, you get a very simple relationship between the gravity pressure pushing down and the energy you get from supernovas essentially scales, or the pressure you get from supernovas essentially scales as the star formation rate surface density. You can then, from this basic thing, you can derive a number of observables. We have the velocity dispersion scaling as one over the depletion time. And to me, this is a very intuitive thing because if you have a region, a little sort of patch of a galaxy, and you increase the star formation rate surface density, you're putting more energy into the ISM, and so it's able to drive more turbulence. We can test to see if this happens, and this is what we did. We compared depletion time to velocity dispersion on a sample of galaxies, and we find an inverse correlation that is quite consistent with the theory. I want to point out that if you want everything to set by things like Toomre style arguments, which are quite popular, it's really tough to get an inverse relationship because at a basic level, under Toomre arguments, if you increase the velocity dispersion, you're stabilizing your disk. So you're decreasing the quickness at which you can make stars. You can then make arguments about disk thickening, which essentially flattens it, but making the inverse power law is quite difficult. When I first wrote this paper, I sort of went to this. I said, I went to Eve and I pointed this out. And also, I guess the problem here is that when you look at the direct comparison, though, of the power law to of the velocity dispersions to what the theory predicts, what the feedback theory predicts, you get a thing that we've known for some time, and that is that the velocity dispersions were quite high compared to the models that generate feedback. And when I took this to Eve and I said, like, look, we get this power law relationship that is qualitatively similar to what you'll get, but we do not get the same velocity dispersions. What is the issue here? Eve is an excellent theorist, and she very quickly told me that your observations are wrong. And what she meant by that is that we were all measuring velocity dispersions with ionized gas because they're quite cheap to get, but that is not the correct tracer to compare to the theory. And in these theories of what's regulating star formation, you have to pay attention to the gas that you're talking about. Ionized gas has already made its stars. It is not about to form stars. But the regulation, the thing that is being regulated, is the collapse of the cold material into GMCs and into star formation. And so you need a tracer that is tracking that. So a low JCO transition is ideally what you want, even if it's harder to get on large samples of galaxies. So this was great. It actually gave me a testable thing that we could look at and see if this, how much this makes a difference. Because we have quite high velocity dispersion, so things like thermal expansion should not be important here. So we used this on we did some observations on the dynamo sample with ALMA to get resolved measurements of CO, where we can measure the velocity dispersion. If you're not familiar with dynamo, in simplest state, it is a sample of disk galaxies, so they're rotating, they're exponential, that have extremely high star formation rates for disk galaxies. Their star formation rates are something like 10 to 50 solar masses per year. The stellar masses of the galaxies are like 1 times 10 to the 10. And this plot shows molecular gas surface density of individual patches compared to stellar mass surface density. And you can see that basically at the same stellar mass, dynamo galaxies are just very gas-rich. And that is the kind of key thing here for this, because they're excellent tests. They give us a large range in parameter space to test these theories. And so we can compare the velocity dispersion of our dynamo galaxies to gas fraction. This is testing this. The red line is for measuring the velocity dispersion with molecules, and the blue is ionized gas. Those lines do not overlap. They do not intersect at high gas fractions, which means they do not intersect at high redshift. And it is extremely constant. The reason, each point here is a galaxy, and the reason there's so many points is because when we first did our dynamo sample, it was so constant, I thought we'd done something wrong, so we went into the literature and scraped out every observation that would be applicable, and it kept getting better. The result kept getting stronger and stronger. When you look inside the galaxies at the resolve properties, that offset is constant at a kiloparsec scale. These are all sort of radial profiles, so you have distance and velocity dispersion on the y-axis, and the different tracers are shown. And you can see it's an outrageously constant ratio across gas fraction, across star formation in the center. It's essentially, the center peaks are from beam smearing. It's not from. And so in the center, it's the same at high star formation rate surface density as it is in the outer parts of the disk. So we can use this now to go back to our test to say, like, okay, how well do the feedback models work, and other models as well, in comparing the the velocity dispersion of the appropriate tracer to the star formation rate. And so here you see molecular gas velocity dispersion versus star formation rate surface density. It's the same plot on the left and the right. And the dynamo galaxies are blue, Fangs galaxies are gray. Each point is about a kiloparsec, a little less than a kiloparsec. And you can see on the left where we're comparing it to two different models. One is feedback only, or they're both feedback only models. One is from the Tigris work, so this is the Ostreicher-Kemp models, and the other is from the Silk. We do get a correlation between velocity dispersion and molecular gas and star formation rate surface density, but it's a very shallow slope on the correlation. And that is exactly what is predicted by the theory, and the 0 point in the scale factor is now there is zero problem with it. The feedback-only models are going right through the data, and the silk simulation, for example, this is just a patch of the ISM, so there's nothing like any kind of instabilities or anything like this. Gravity is obviously there in a potential form, but there's no extra effect. It's only feedback that is driving the gas and the velocity switch. So because of that problem I talked about in the beginning, many people came up with a lot of theories about creating extra sort of things like gravity, introducing extra properties. You see those drastically, this is a theory by Mark Krumholtz, and you see it drastically overpredicts the velocity dispersion of the molecules because it's missing the scale factor. This ratio between molecular gas and ionized gas velocity dispersions, it seems to be constant across a large amount of the universe. There's simulation work from the Silk team and also the Ventergarten team. I really like this figure because you can just see it with your eyes. The molecules not being heated in the same way as the ions. You can look at the disk thickness of the Milky Way and ionized gas and the molecular thickness. You can make some very hand-wavy assumptions and turn that into velocity dispersions. You get a bang-on, quite similar ratio between the two. There's a couple lens galaxies that have been measured. They find the same thing. And then finally, the FANGS team did velocity dispersions of H2 regions, and they get basically the same results. So across a large amount of environments and properties, everybody finds really the same relationship, the same ratio of something like 2.5 that has these. So in terms of what we want to learn about feedback, there's really two things. First is if you're going to go off and try to measure turbulence through the velocity dispersion and compare that to models, you have to take in these multi-phase properties of the velocity dispersion. You don't have a turbulent velocity of a galaxy if you only have one tracer. You have a turbulent velocity of that tracer in the galaxy. And this also means that there is this difference in scale heights of the gas, and that if you think feedback is doing this, this is telling us something about the way that feedback couples to that gas and how it works. So I'm now going to switch gears and talk about the M82 wind. And so this is this sort of gorgeous picture we've known for years. The red here, this is PAHs from Spitzer data. And the blue is X-rays. And it has been a problem for a long time to explain why that red light is there, why the cold gas actually exists in an outflow. And the reason is that that's been really hard is because when you explode your supernova and that hot gas interacts with the cold gas, it destroys the cold clouds of gas because you sort of get this little globule of Kelvin-Helmholtz instability. But the gas is there, which means we don't understand our models for outflows. And that is a real problem because as we talked about this morning, the sort of survival time of gas outside of the galaxy is basically what's setting your true mass loading, right? You can have a huge amount of gas leave a galaxy, but if it falls back down immediately, then that's not very much mass loading. So you need to understand this model for what's setting this in order to understand all these estimates. So several years ago, Max Giunchi and Pang O came up with an idea to solve this cloud destruction problem. And it is that basically if you have your glob of gas, so these are two separate runs of a simulation where it's a very idealized situation. You have a wind tunnel of very hot 10 to the 6 Kelvin gas going across your cold cloud, and you get this Kelvin-Helmholtz instability. And on the left side, that's what's happening. You're destroying the gas. But on the right side, what they've done is incorporate rapid cooling. That it's physically realistic, but it is just very fast. And they've said if there's a cooling layer within the cloud that can, ooh, no. If there's a cooling layer in the cloud, then you can overcome this cloud destruction problem. This is great. Theorists love this. There is a million simulations, but there has not been any direct observations of these cold clouds, so it's completely untestable. Until this year, when we got JWST observations of the M82 outflow. The first set of observations we got are just of the center, and so that's what we're showing there on the right-hand side. What the red, if we can see it in there, is the PAH, the 3.3 micron PAH emission. And we get a resolution of about a parsec on the individual clouds in the wind, and that is really great because we can resolve the structures that people claim they're seeing. And what we can test with this data set, what we can specifically test is the breakout of gas from the disk. We will determine if it is consistent with a scenario in which that gas survives that breakout. So this is just the data again, and what I want to point out is if you keep zooming and zooming in, you get something over on the right, on the far right, which is a structure that we decided to our eyes looks quite similar to what is in these wind tunnel simulations, where you have the bright part at the bottom and then you have this like stretched out cloud of gas. We went through and then found several of these in the data. And what you want to do is if you can measure the size of the cloud, and if you know you have a decent estimate of the kinematics of the gas, you can turn that into a time scale for destroying those clouds. It's called the cloud crushing time scale, and it comes from some fairly basic assumptions about the Kelvin-Helmholtz instability. So it's the time scale for the gas, for the hot gas, to mix fully with the cold gas. If that time is longer than the travel time, then that is at least consistent with that cloud not being, it is possible that that cloud was not destroyed. And that is what we found. What we found is that the cloud crushing time for our clouds was something like a few mega years, whereas the travel time was more like half of a mega year. And then we also compared it directly to results from Drummond Fielding's group to exact simulation. And finally, this is my last science slide. We can compare it to the X-rays. I won't go through this in detail. I'll just sort of say what the result is. That we found that the multi-phase properties of the gas are still quite important here, because where that blue gas is, where the X-rays are where the pHs are not. And we find that that setup, which we've known existed forever, basically starts instantly as soon as you leave the disk. The pHs start separating. And what this means for the cloud survival is you're surrounding cold gas with other cold gas, which makes it easier for them to survive. Okay, so that's it. Basically the top of the talk, I think the one takeaway is that ionized gas and molecular gas dispersions, they represent a range of different descriptions of the turbulence, and you should think about it all. When we go to the second half, it's not super conclusive. We've sort of said that the clouds we're seeing are consistent. I think this is more like an opening of a door, that we are now on the same page with people who are simulating outflows. This is an 11 micron image of the full wind that we have for M82. In cycle 3, several more winds were observed. So this fine scale detailed comparison to the simulations is now something that we can make into a little bit of an industry. And I'm quite hopeful for how that will play out over the next few years. Thank you. Sorry.
We have time for a few quick questions. Yes, please.
Hi, thanks for the very nice talk. So your star formation rate velocity dispersion plot, especially for CO, I noticed that the range is actually very high compared to the bulk part of disks in nearby galaxies.
Say that again?
So the velocity dispersion, the range you plotted seems the velocity dispersion you plotted is very large compared to the bulk gas in disks of nearby galaxies. So I'm wondering about the bias in your sample. Oh. Are you picking up the parts which are likely affected by feedback?
So,
because the plot seems to be driven by that part of...
Oh, the sample is 100% biased. It is a biased on purpose sample to do this plot. Yeah. And so it's the galaxies, so first of all, the high velocity dispersion is not like a property of a region of dynamo galaxies. The whole galaxy is gas rich, and the whole galaxy has high velocity dispersions. And so this is why we selected them, because if you use the FANG sample or something like that, FANG's galaxies are all selected on purpose to be basically the same galaxy at a different mass. And so we need these high gas-rich galaxies in order to get enough parameter space to test them. So it's the comparison of the two is what's important.
So in that case, the result is more like if you take paths which are affected by feedback, and then it follows the predicted feedback model, rather than the bulk gas follows.
So the whole thing is affected. The whole galaxy is consistent.
The dynamo galaxies.
And also FANG's galaxies. Yes,
Okay.
that's what I think we're going to hear about the JWST stuff and about the small scale H2 regions affecting their part around them, is that they think that feedback is setting the turbulence. And I think that's on more secure ground than the high gas fraction systems, that feedback is driving that turbulence.
One last quick question and answer.
Yes, please answer it for me.
Regarding the M82 cold clouds, have you been able to determine the mass?
No, that is, so with PAHs, I mean, they're basically just not a mass tracer. Even if you wanted to trace the mass in PAH form, you're only like 3% of the dust mass, and then scaling that and doing any of those scaling relations in an outflow compared to a real galaxy. No, that would be nice, is basically, yeah.
Okay, let's thank Diana again. And our next speaker is Angela Adamo.
Much shorter, okay.
And she will give a talk on star cluster formation and evolution across cosmic times.
Okay, almost there, yes. Good afternoon, everyone. I can say it's nice to be back in Italy. And to say that, I would also like to thank the organizer to give me the chance to present you some of my latest work in the context of what is happening in the field. So yes, I'm Angela Adamo. I'm associate professor at Stockholm University, so I come from a very cold country. And a warning that this is going to be a talk about very small physical scales. So we are moving essentially from galaxies as units down, 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 down to star clusters and association H2 regions. And if you are a bit lost, just to give you a reminder, this is a beautiful dwarf galaxy. It's actually a dwarf irregular. And all the action in this dwarf irregular is happening within 1 kiloparsec. And you see a lot happening within this region. We see globular cluster, which are remnants of relics, right, of past starburst. And then we see still young star cluster forming. This is really massive. I mean, consider that in this galaxy there is 1 10 to the 6 solar masses cluster. Star formation rate is not that high, but the gas has been compressed and that cluster has pushed and created an H2 region. So I will not have time to give you a full overview of small-scale star formation. It has already been introduced, the topic this morning, by Rob. So I will just move into the emergence phase, because it's what we are trying to do now with JWST. So if we look at this beautiful cartoon of the simulation, which have already been presented several times, I like it very much because it shows that stars essentially, we are moving in age, and each panel is essentially a snapshot into these star-forming regions where stars are collapsing. And here it shows density and temperature. So we are looking at the densities which are becoming increasingly lower as stellar feedback starts to remove and so affect the gas, right? It's ionizing the gas, is giving momentum, so the gas is also pulled out, creating what we would call a classic H2 regions. And then if you look at temperature, we see that the gas is becoming increasingly warm until the supernova explode, and they are essentially affecting not only the gas, as we usually think as H2 region expansion or removal of geomolecular clouds left over, but it's also affecting the entire ISM in the disk direction. So if we look at this from the very small scales, and what we have been doing so far, using Hubble and looking in far galaxies beyond our local group, let's say, is we have been looking at H2 regions with stars within them, while we have been just at a biased view of this phase. So the phase when stars are already in the main sequence and they start to ionize the leftover gas. So we see an H2 region, we see a photodissociation region surrounding the H2 region. And, sorry, wrong direction. And then, of course, we had, again, so we have seen with ALMA the earliest stages. So what we have missed so far is the link between this phase and this phase. And the question is how long it takes, essentially, to go from collapsing geomolecular clouds to exposed H2 regions. And again, these scales, as we heard this morning, are very important because essentially they set the star formation efficiency of the cloud. They also determine how long it takes to disperse the geomolecular clouds, and then as well, so where the feedback from stars is going, because once the low density channel are evacuated, that feedback is leaving the region and affecting the ISM of the galaxies. So with JWST, we have been looking at the H2 region. These are already past work. And essentially what we can do is we can look at morphologies and say that there is an evolution, right? We can quantify this using star cluster ages within this H2 region. And what we have concluded with the study on AGST essentially is that this emergence phase takes roughly between 2 and 5 million years. And you can see also work that Andrea presented a few talks ago this morning, where these time scales are also quite short, okay? But of course, this is because we have been looking in the optical. So what happens when we look where the embedded star clusters are? And so the prediction is that we should find really there. We should nail down these time scales. So we see that some work has already come up from FANGS and GOLD surveys where they've been looking for embedded star cluster in spiral galaxy, and these are LERGS galaxies, so the highest starburst system we can find in the local universe. And the different methods have been proposed to actually find this embedded star cluster. In this work, they concluded that the time scales for emergence are very short, roughly 1 to 2 million years, while in this work, you see that they select a region where they expect the very embedded star cluster to be. And then the star cluster has to do all the work to come down to where we see the optical cluster. So in my case, we have been focusing on studying the emergence phase using the FIST sample. FIST stands for feedback in emerging extragalactic star cluster. So this is a beautiful picture of M83 with the JWST bands. I also would like to thank with M51 background, which is always astonishing, my collaborator. And then, yes, let's move on into the FIST project. So essentially, we have selected several broad and narrow bands. The narrow bands give us Paschen alpha, bracket alpha. We have a pH at 3.3 and a 7.7 micron emission. Actually, we have pH also in the 560. But for the talk, we will focus mainly on the 3.3, and then we will add some 7.7 pH tracer. So the data are all in. As last week, we got the final mirror observation of this dwarf galaxy. The sample has sampled galaxy within 7 megaparsec. You see here M83. You see two dwarfs interacting here. So apologies, the data are not ready for this. They came just 8 weeks ago in. Then you see NGC 4449, M51, and NGC 628. So if we focus on NGC 628, which has been a bit the pig, or the guinea pig, where we have been kind of developed the method to find what we call emerging star cluster, we look essentially at regions here where the 3.3 micron is very extended, but also peaked, and several regions we see, these are the green dots when we use the bands. And we see also that where most of the peak in the tracer, this is Paschen alpha, I will clarify in the next slides, we see that also GMCs are still, the gas is still very dense in these regions. So how do we extract what we call EYSCs, emerging young star cluster? We use tracer of star formation. So we extract peak emission, compact peak emission in Paschen alpha, bracket alpha, and 3.3. And then when all the three tracers coincide at this resolution, we are talking below 10 parsec resolution, we call them EYSC1. We have a category of peak in emission where we don't see anymore the 3.3 micron. Those are the EYSC2. And then we have a category like this object here, where we see the peak in only Paschen in PIH emission. And of course, we know where are the optical cluster in this data. So if we look now at the sequence, and apologies, the plot is coming. So if we blindly extract everything in the field of view, we get thousands of objects. We have almost 100,000 here. We see these are the evolutionary tracks for optical cluster, and here you see are the evolutionary tracks when we include the PIH emission in the 3.3 micron. And you see that all the extracted emerging cluster lie in this sequence. We blindly use the gray dots to actually find the embedded star cluster using the Linden proposed method, and we find that very few % of them were missed in our selection, which is also important. And then I can put this emerging star cluster in the context of YSO color, and then you see that actually where we have the most, the EYSC1 and the embedded phases, they overlap with EYSC color 1, and the other phase overlaps with EYSC color class 2. So we see essentially an evolutionary sequence. This is a work then that we have been doing with the master student Alice Knutas in Stockholm. She has actually extracted all the EYSCs in MD3. You see in cyan, and also you see the blue. Unfortunately, the contrast is not very high, but in blue it's all the regions which are UV bright and where we see the optical cluster, while all the EYSCs actually trace the dust lane in the galaxy. So we have done ACD fitting with Seagull, and then you see that all the EYSC population is very young, and it complements the distribution in ages of the optical cluster. The extinction is much higher for the EYSCs with respect to the optical cluster, while the mass function is identical. So we are looking essentially at different phases of the same cluster population. We have also been looking at different EYSCs in the different regions. Sorry, the contrast is not very high, but we have spiral arms, and then we have the bar, the center, and the interarm regions don't have a shadow. And you see that the mass distribution are also different, and the center, we know there is a star bar, is where the most massive clusters are. So to wrap up, here what we see, when we have been so far analyzing M83 and NGC 628, we see that the deeply embedded phase, when there are no massive stars already ionizing the gas, is very fast. Because when we use the ionizing gas as a tracer, essentially we extract at least 90 to 95% of them. And then this cluster, this emerging phase, is longer in the phase 1, while it's really short. So once the PDR are destroyed, because we know 3.3 emission is not there anymore, so this phase lasts very short. So if we put this into a cartoon, we can say that overall, this emerging phase takes up to 5 to 6 million years. And then it overlaps with the optical cluster at a certain ranges. And so the question here, what we are trying to answer is, do we need supernova to really make the cluster emerge? Actually, not really, because if you think that the majority of the cluster are between 10 to the 3, 10 to the 4, these are clusters which do not have really massive stars. So the first supernova exploding will come not a 4 million year, but later. So it's this supernova delayed explosions, right? So essentially what we see is that we confirm the time scales. They are slightly longer. We expected that because we missed all the embedded phases. But essentially we know the photoionization, it's enough to actually emerge. So we have been doing more, of course, looking at embedded star cluster. Here, this is work done by Ben Gregg at UMass. Ben used the EYSCs to actually calibrate the 3.3 pH emission as a tracer of star formation rate. And what you see here, so these are the results for NGC 628. Well, this is the relation proposed using Akari data. And this relation seems to be linear with the infrared emission, so measured from Paschen alpha, bracket alpha. And what we see is that actually when we look at these regions is sublinear. We think essentially if we zoom in into the region that here PIH are already destroyed. We are looking very much close to the stars which are ionizing. While in this, here in this region, all the dispersion we see is because of stochasticity in the IMF for the star cluster. So then we can move on, and this is work that Alex Pedrini has been doing in Stockholm. We actually look at the morphologies of PIH. We select all H2 regions which are very compact in appearance in the Paschen alpha, and then we look at the PIH traced by 3.3 and 7.7. The contours show you the CO in the region, and you see that we see actually an evolution in the PDR traced by the 3.3. So we see a compact PIH morphology which coincides with EYC younger than 4 million years. We see an extended, so you see the profile here becomes already more extended than the ionization tracer. And this phase is roughly to coincide to cluster with the 4 to 5 million years. And then we see open PIH. So the PIH now has become a donut, where this is where the peak in Paschen alpha is. And these are the regions with older ages. So we also looked at PIH ratios for this region, and we see that in all the morphologies, this ratio is constant. It's definitely lower than when we look at 50 parsec scales or we look at galactic scales, and it's definitely lower than prediction from model, even when we just use neutral PIH in the models from drain. And we understand this as the fact that it stays constant as an evolution. So here we see the PIH emission as a function of the age of the ionizing source within, and we see the emission is decreasing. So PIH emission 3.3 and 7.7 is destroyed, and it's destroyed at the same rate, because then when you look at the ratio, that ratio stays constant. So now we switch gear, and I think Rob would have given me a PhD because I look at star formation in local galaxy, but I'm going to look now very high redshift. And we look, essentially we ask the question when and where the first star cluster form, okay? And to do that, we need to start from lensing, right? We need magnification because we want to see at the highest physical scales where stars are in these galaxies at high redshift. And secondly, so if we go back to this charter, we see that when we use lensing, we usually go down to sub-100 parsec scale. Then we are looking at the entire H2 regions. And then depending on lensing or depending where you are in redshift, you can resolve down to a few hundred parsec. And finally, the typical size that you get when you look at clumps in galaxies at unlensed field. So JWST has showed us already from the first images that actually galaxies have a lot of clumps. These clumps are very small, and in some cases it has shown us a globular cluster surrounding galaxy at cosmic noon. So this is a work which we have conducted with Adelaide in Stockholm. You see the gray contours show HST analysis of stellar clumps, and the circular showing you where are the clumps we extract from the SMAX 0723 field. We are essentially going down in luminosity, so we are more sensitive, and we have a 3 times higher resolution. So you see the peak of this sample will be significantly lower than HST here, and then moving here. And this is totally depending on the lensing, of course. And since we have the optical now, we have a better ages and masses estimates. So we looked at the sparkler. This is the galaxy with the globular cluster surrounding the field. Essentially, we are looking at the galaxy, if you want it easy, which is roughly 8.8 gigayear after the Big Bang. And then we are looking at star cluster that actually formed at the early ionization, okay? And these globular clusters are surrounding the galaxy. I will skip the metallicity age analysis because I think I'm running almost 5 minutes, but still have a lot of slides, okay? So, but I focus on Abel 2744, which is the most recent work that Adelaide has dedicated their effort. There are a huge amount of public data on this galaxy cluster. The first are from Uncover, and then recently also from Mega Science. So you see 18 bands to study stellar clumps at high redshift. And this is the image from the Uncover team. And here you see an inset of the different galaxies we are looking at, all with the disk morphologies, more irregular morphologies, and moving higher and higher in redshift, up to redshift 8, where they become really compact. And what we see, so this is kind of the sample. We have 500 galaxies between redshift 1 and 9. 40% of the galaxies are confirmed spectroscopically. We extract more than 2,000 clumps in this magnification range. Here you see, this is a dream coming true, even for someone doing star cluster in the local universe. What a stellar clump light looks like in 18 JWST bands. Since we have a medium band, we are really sensitive to emission lines, so the ages are really nailed down. So we are sure about the ages, we are sure about the masses of these clumps. So for the context of where star clusters form in these galaxies, so here you see the size versus the star formation rate density of the stellar clumps, and you see that there is a gradient in color. As we move at higher redshift, stellar clumps have a higher star formation rate density for the same size, okay? So it means they are producing more stars in the same regions. And then if we want to look as a function of galactocentric distances, and now the color are still per redshift bin, you see that the clumps which are in the galaxy just after cosmic noon are on average older than clumps which are in galaxy here at before cosmic noon, right? So we are looking between redshift 3 and 5. We see also that the fraction of mass, stellar mass in clumps is actually quite high, and is highest so in the pre-cosmic noon galaxies with respect to the after cosmic noon ones. And we see also that the star formation, so the stellar surface density of these clumps is really high. So if you want a star cluster in the local universe is roughly 10 to the 2 in solar masses per parsec square. A globular cluster is here, and these clumps have sizes of 100 parsec on average. So if we want to summarize, essentially star clusters are forming in stellar clumps, which are increasingly high in star formation rate density and stellar surface density. They are increasing younger. We are looking at galaxies which have an increased higher, lower specific star formation rate. And they becomes also, we see more massive clumps within the inner regions of the disks. So we have also been seeing first star cluster. This is the sunrise arc at redshift 6. We are really at the edge of reionization if we start from 0. And we see essentially in this galaxy there is a star which has been well studied, but there are several nodes. And you see these 2 nodes are here, UV bright and optically bright, but there is not really much emission. In fact, they appear to be slightly older, but they are very compact and they are gravitationally bound. We know that their crossing time is very small with respect to their ages. So we know that these are really genuine protoglobular cluster. We see star cluster embedded in star-forming regions. These are the very high equivalent width that we measure in bursty galaxies in reionization era. They have a star cluster within them. And then I think I will conclude. My last, 1 minute, is the discovery essentially of this redshift 10 arc, which has recently been observed with JWST observation. You see that is a dropout in the bluest JWST filter we have, but then we see the arc appearing in the F150W JWST filter. So this is really the far UV light of the galaxy, and summed with all the optical up to B band. And you see we also find the counter image of this arc. This is the redshift estimates, which is, we are quite confident about it. And this is the arc light. Now we are focusing into the core of the galaxy, and we see essentially, if you look actually here, 5-star cluster, better maybe here in this resolution. They are labeled. And so this region in total, if we look at the source plane reconstruction, is roughly between roughly 50 parsec. It contains a 5-star cluster of 10 to the 6, quite young in their ages. And it's quite amazing because the far UV intrinsic luminosity of this galaxy, it's really low, it's minus 17.8. So we are looking at the range of the faintest galaxy we are able to reach in the field with JWST, even in lensing field. What is important, I will go 1 minute over time, sorry. It's when we look at the physical properties we derive stellar density. Stellar density, you should think it's insensitive to the lensing, we are assuming. The stellar density of this cluster are really high. Here, these gray dots are the globular cluster, and this is the cloud of local star cluster in the local universe. So they are very dense. And essentially what we think is happening is that as they form, right, these have formed roughly 450 million years after Big Bang, they have a Hubble time to expand due to different mechanisms. And then they are important because essentially when you have such high stellar density, you can have runaway mergers, either of massive stars or black hole in their cores. So we are looking at seeds of black holes, intermediate mass black holes. We are looking at where very massive stars are forming in these very early galaxies. Okay, and I will stop here. These are my conclusions. Thank you very much for your attention.
Thank you. Questions for Angela? No questions?
About the last part of the seeds of the intermediate mass black holes, so that would go into the direction of finding intermediate mass black holes in the globular clusters, or also, for example, of the Milky Way, which is a hot topic, let's say, given the difficulties in observing them.
Yes, for example, but also you should think we are looking at Redshift 10, right? This galaxy will be accreted, merged with other galaxy, right? So they can be also progenitor of black hole, then they will grow into galaxy black hole mass. Yeah.
Thank you, Angela. Great talk. So you were saying that they will have this high redshift cluster, they will have time to expand, but so do you think they need a long time to expand, or will they be destroyed before?
So it's a different mechanism, right? So I think the slowest will be relaxation, because it depends on evaporation, right? So, and that is the slowest mechanism, but still this is Hubble time. So it will be plenty. Stellar evolution and the black hole dynamics in their center, stellar black holes, will be the most rapid to start to explore, extend the cluster.
We have time for one last question. Yes, please.
So I was just wondering, by the end of your talk, you said something about intermediate mass black holes. Could you say a little bit more about that?
Yeah, so essentially, when you at these very high stellar densities, what happens is usually due to N-body interaction, black holes we think are ejected from the star cluster at the density we see in the local universe. While when you have such high density, actually models show that they sink and we start merger. So what happens is we have seen a stellar black hole mass, we have seen a galaxy black hole mass, but we need the intermediate phase, which we think are the one that will grow to become very massive black holes, right? And this goes also in the scenario here you see of the seeds for the many AGNs we are finding down to Redshift 5 and 6. Where are the seeds of this black hole coming? And essentially, so far we have assumed that direct collapse black hole and the stellar remnants from POP3 are the most likely scenario. But actually, if the star cluster in Redshift 10, 12 are so dense, it becomes also a viable way to produce them. So, yeah, welcome.
Okay, let's thank our speaker again. Thank you. And our next speaker is Giunchi. And he will talk about star formation in young stellar clusters of ramp pressure stripped galaxies as seen by HST.
Whoops. Maybe I should. Wait a second. Okay, sorry. Didn't do it before during the test. Okay, yes. Hello everyone. So what I'm going to present today is essentially a very brief summary of the PhD work that I have carried on with my supervisors in the GASP team. So many names should be familiar right now. And so in general with the whole GASP team and also with other professors and doctors. And they are essentially published in these 4 papers plus some upcoming works. So, as the title suggests, and I will go straight to the protagonist of the talk, the focus of my work was the study of the stellar clumps, so as Angela was saying before, objects with sizes of hundreds of parsecs, let's say, from 100 and more, in these peculiar objects which are the jellyfish galaxies. So as said this morning, galaxies that have been recently accreted by galaxy clusters, so they are experiencing the ramp pressure stripping of the intracluster medium. The interstellar medium is stripped far away from the disk, and there is evidence of ongoing star formation in the stripped gas. You can see also here, this is the HST dataset on which I worked. In blue, you can see the star-forming clumps, not only in the disks, but also in the tails of these objects. So the idea essentially is to study these clumps and compare them with the samples that we have in literature for other main sequence galaxies or starburst galaxies, looking for differences caused by the fact that these clumps are in a very peculiar environment. They are born from stripped gas and embedded in intracluster medium far away from the stellar disk. So to give some details about the data set, the resolution of HST of 70 parsec is enough to have an estimate of the size of our clumps, and the choice of the photometric bands is good to distinguish different ages of the stellar population, thanks to the U and B band, or the two bands on the left, but also we can use the optical bands, including a narrow band filter, to extract the H-alpha line. So essentially we have two tracers of star formation, and we are able to trace star formation on two timescales, 10 megayears for the H-alpha and 200 megayears for the UV. So we can also study the spatial evolution of star formation. The clumps were detected with Astrodendro, both in H-alpha and UV. This is the example of JO201 in H-alpha, so the galaxy that was on top left before. And as you can see from the colors, they were divided in three main categories. The red clumps are the disk clumps, essentially undisturbed, while the blue clumps in the extraplanar region are still inside the optical disk, but already born from stripped gas, so already disturbed, while all the green clumps are outside from the stellar disk, so of course born from stripped gas. So we have these three different categories and environments. Plus, in the tails, we were able, since we are far away from the optical disk, to detect structures, we call them star-forming complexes, also in optical bands. This is fundamental to, let's say, recollect the whole stellar amount that was formed from the stripped gas, because we can trace also older populations. You can see them here in violet, nicely matched to the gold H-alpha clumps and the UV clumps in purple. So we are able to really reconstruct the whole stellar, the whole gas that went into stars from the stripped gas. So this is the size of our sample, to our knowledge the first statistically relevant sample in this kind of objects in jellyfish galaxies. So 2400 H-alpha clumps, 3700 UV clumps, and 400 optical complexes, with a good amount of them in all the spatial categories. Even though when we need to study the sizes of these objects, there is an important cut because we need to require the core radius to be larger than 70 parsecs, the resolution of HST. And so essentially the sample is much smaller, but still there is enough statistics in all the categories to perform some studies on the population of clumps. For example, the luminosity size relation of the H-alpha clumps. You can see them here, the three different colors of the three different categories. And the interesting thing here is that they all occupy the same relation. They are in the same region. So this means that the tail clumps that are far away from the disk, embedded in intracluster medium, born from stripped gas, show similar properties to the disk clumps that are still inside the disk, and so in conditions which are more similar to those met in main sequence galaxies. Furthermore, if we compare our results with literature samples, so clumps in main sequence galaxies in black, this is the SINGS sample, and the clumps of the Dynamo sample of which Diana was talking before, we can see that there is an enhancement in H-alpha, and most likely also in star formation rate surface density, for our clumps, even if the enhancement has not the same amount observed in the clumps of starburst galaxies. This makes sense because we expect ramp pressure stripping to be able to compress the gas, even if it's not a process as violent as a merger, for example, which is able to trigger the starburst mode, or, for example, the turbulent disks that we have at higher redshift. So we think that, let's say, this is a nice result because it's somewhat expected by the entity of a process like ramp pressure stripping, which can disturb the gas, but not as a merger or a starburst mode. Then, thanks to HST, we wanted to study also the morphology of the objects, especially in the tails, because as you can see here from these RGB images, you have in red the H-alpha emission, which is often associated to a UV tail, often pointing, let's say, typically pointing towards the disk. Here, in this case, it's particularly evident. This has been observed in the last decade. The first description of this process was done by Kinney in 2014, and they are the so-called fireballs. Essentially, the interstellar medium is stripped in position 1, for example. It forms a population of stars, and then it's pushed away in position 2 by the intracluster medium, and so essentially it forms in position 2 a younger population of stars. So we expect essentially a trend of the age of the stars with the distance from the galaxy, in a scenario in which young stars are displaced farther away from the disk than the old stars. And to have a systematic evidence of that, we took our optical complexes and we computed the so-called displacement. So there is the UV displacement, so the distance from the center of the brightest UV clamp, and the H-alpha displacement, so the same thing about for the H-alpha clamps. And essentially we expect to have a larger displacement for the H-alpha clamps because they are tracing younger populations, so we expect them to be more displaced than the UV. And we do see it. Here you can see in golden the H-alpha displacement and in red the UV displacement for correlated to the area of the complex or the axial ratio. And you can see that the displacement increases in large and elongated complexes, but in all situations, in all the complexes that we have, there is a systematic larger H-alpha displacement than in the UV. So it's the first systematic evidence to us of fireballs in these galaxies, because we were able to find this evidence by defining a common properties for all the complexes without looking at the single structures one by one. And this is important if we want to increase the sample, and so we can't keep looking at each of them one by one. So we need a quantity that can get over the peculiar morphologies of these objects. Finally, as an ongoing work, we are studying the mass functions of this complex. Masses and ages are published in this work by Ariel Verle in 2024. We fitted the SCD of our clamps with backpipes. This is a UV clamp, for example, so we have the estimates of the properties of the stellar populations of the clamps of our sample. But to study the mass function, we need to quantify two effects that can bias our results. So the completeness of the sample, essentially we can lose low mass clamps because they are fainter, and we also wanted to test the result of backpipes to understand if they can give a good estimate of the real mass of the clamps. So we created a mock library of images of clamps that we treated like real clamps, but we know a priori the properties of the mock clamps, so we can compare input and output essentially. These are the two results, so the completeness on the left, as expected, there is a good completeness at high masses with a drop at low masses, while the comparison between the intrinsic mass of the mock clamps and the results of backpipes show that there is a good agreement at high masses with a slightly discrepancy at low masses, but essentially the idea is that for each observed clamp with a certain observed mass, we have a distribution of possible intrinsic masses that we model as a Gaussian distribution. So we can recover the likely, let's say, the most probable intrinsic mass of the clamps. The mass function was fitted with, in a Bayesian way, so without going into the details of the likelihood, for each clamp we have essentially three components: the mass function that we modeled as a power law, the Gaussian distribution, so the distribution of intrinsic masses at a given output mass, and the completeness of the sample. So for what concerns the tails, I will show the results for the tails. We find that in H-alpha the slope is consistent with 2, with a slightly steeper slopes in UV. This is very interesting because the slope equal to 2 is what is been observed and also simulated for main sequence galaxies, and so it testifies that also in the tails, so clamps born from the intracluster medium, from the stripped gas, etc., the mechanism that is forming the clamps is the same observed in local disk galaxies, for example, while the steepening in UV is somehow predicted by models of clamps evolution and aging. So just leave you with the summary, and thank you very much.
Thank you very much, Eric, for this interesting talk. Questions?
Sorry. Eric, did you see any mass difference between the UV and the H-alpha clamps?
Yeah. The UV clumps typically are more massive, especially if we match them. The H-alpha counterpart of a UV clump is slightly more massive.
So is this predicted in the fireballs, like that you should have that the mass of the youngest clump cluster is becoming?
Yes, because with the UV, essentially we are collecting, you can see it here also, the UV is tracing stars as old as 200 megahertz, so including also the stars that we detect in H-alpha. So it's like not only the stars older than 10 megahertz, but younger than 200. We are including all the stars older than 200 megahertz. So typically the UV clumps contain also an H-alpha counterpart if there is ongoing star formation. Then there are also cases like here in which probably there was recent star formation but not ongoing, so there is only the UV population and no very young stars.
Any more questions? Yes?
Earlier in the talk, you said that when they move out of the galaxy, the clouds, I think you said condense or become more compact. Is it that they're actually becoming compact, or are you really just stripping off the more diffuse layers that surround it, and so what's left looks more compact?
Yeah, what we think is that the gas compression happens in the very early stages of the RAM pressure stripping. So when the intracluster medium really firstly impacts on the interstellar medium. So that's why we think that's the reason for which we see, for us at least, the enhancement also in the disk clumps. Even if they're not stripped, there is the gas compression. Then in the tails there is also a matter of recycling of the interstellar medium that, let's say, considering the distance at which we see some clumps, it seems that the stripped interstellar medium is able not only to form a first generation of stars, but also to collapse again. So in that case, the compression of the RAM pressure stripping maybe is playing a minor role in this sense, because it's a subsequent process after the stripping and after the production of the first populations.
Okay, thank you very much. So let's thank Eric again. And our last speaker before the coffee break is Diego Falceta Gonçalves. And he will talk about star formation in turbulent magnetized medium, I believe.
Yes.
Okay. I'd like to thank the organizers for giving me the time for this talk. In this talk I will show you some results from numerical simulations of star-forming regions. The idea is to study the dependence of two important parameters, which are star formation efficiency and star formation rates, as dependent on some of the turbulent parameters, specifically the Mach numbers, sonic Mach number and Alfvénic Mach number. So this is an old view of star formation. That's a roundish cloud that may be collapsing because of gravity, and eventually the Jeans length will reduce so much that this cloud will fragment, and these fragments will collapse and fragment individually. And this should go forth until the stars form. However, it has been thought for many, many years that turbulence and magnetic fields, they are collapse preventers. And what I will show is a different picture. We know that the ISM is highly turbulent through many, many scales, from hundreds of parsecs down to milliparsec scales. And at large scales, the turbulent amplitude is in general supersonic by a factor of 10 to 30. So it means that the sound speed is 10 to 30 times smaller than the motions of the gas. Because of that, you expect to have shocks and the formation of dense structures. Moreover, what turbulence means is that the energy that's in a given scale may be transferred to smaller scales through wave-wave interactions. This can happen in subsonic turbulence, which is basically the Kolmogorov theory, but also in compressible turbulence, which is the supersonic case. In this case, the energy transfer rate is a bit faster through scales because of the compression as well. So usually there is some fight in the literature because authors try to prove that the turbulence in the ISM is Kolmogorov-like, so they search for the 5/3 slope, but usually what they get is something similar to Berger's turbulence, which is -2, and they are very similar, so because of observational bias or schematic errors, usually you cannot determine which one is which, but basically on the physics, what you expect is both. It depends on what you were probing. If you are probing compressible gas, it should be more Berger's-like, which is -2. And if you are looking at the incompressible phase of the gas, of the turbulent transfer rate, the slope is closer to -5/3. When you put magnetic fields, everything goes more complicated, because then the energy can be transferred through scales, not only due to acoustic waves or shocks, but also by Alfvén waves. There are many, many different modes. In the single fluid, most common case, you have 3, the slow, fast, and pure Alfvén modes. But when you consider electrons as well as a different fluid, or diffusion parameters between parallel and perpendicular orientations of the field, the universe of possible modes grow, and then the turbulence energy cascade becomes even more complicated. But what's important about the turbulence cascade is that what people typically assume that turbulence is based on observations, which is the dispersion of velocity, is in general not the turbulence itself. What you see sometimes is the dispersion of velocity of individual cores or clumps, which are not related to themselves. In the turbulence, what you have is all scales are connected, and this is different to what most of the observations tell us. So in general, the turbulence that you measure is not the turbulence, it's the dispersion of velocity of individual cores moving in relation to each other. This is what's shown here for M51. This is the pulse data, but you can also take the data from Dian's talk as well. So usually people relate the turbulence to the dispersion of velocity, and the dispersion of velocity is also related to the star formation rate. This is a chicken and egg problem, because if feedback is more important in the distribution of velocity of the ISM, what you have is that the star formation rate is responsible for the dispersion of velocity. But as I will show, the star formation itself is dependent on the turbulence level. So this could be the opposite. It could be that a more turbulent ISM will end up with higher star formation rates. And this is what I'm going to show. Why turbulence is related to star formation then? Because if you have supersonic turbulence, you end up with compressions which will give density above a critical level, considering typical Giunchi's mass. And these individual regions, they can become gravitationally unstable. This theory has been done analytically, but the previous papers, which are shown on the left, they do not consider the sizes of these regions. They just consider the PDF of density in order to estimate the mass functions. Patrick Hennebel and Chabrier in 2013, they provide a more realistic scenario for the analytical mass function of the cores based on a pressure-checked type of modeling, where you determine if these peaks in density, they are near or far away from each other. If they're too far from each other, they cannot form an object, collapse. If they are close together, you end up with a critical mass and collapse. But basically, when you observe the PDF of the density in the ISM, what you expect is that the high end in density should form these stars, but not all of it. Okay? Do I have 2 minutes? Ah, okay. Okay. So this is the scenario that we think we have. So we have turbulence being driven at very large scale due to galactic motions. For instance, we have simulations of plumes and gas arm interactions that drive several decades or hundreds of parsec scales turbulence, which will then downsize to parsec scale for the molecular clouds, and these will form the filaments as I will show, and which will then form the stars. In order to study the role of turbulence and the magnetic field in the star formation, we need a large number of numerical simulations. But the main problem is that the resolution usually is too coarse, so it's very, very expensive. So we did very high resolution, just a few. We have 6 very high resolution models. These are not AMR, these are fully 2048 cubed models. These are the initial conditions, and this is the outcome for different times of the simulation. The parameters above are the sonic Mach number and the alphenic Mach numbers. So this simulation is a supersonic and superalphenic. This means that the magnetic field, the mean magnetic field, is not strong enough to change the turbulent distribution of velocities. This is just a projection of the velocity field on top of the density, and this is the prescription for the identification of the cores. So what we do, for each cell, we determine the gene's radius, and then we calculate the mass within, and then we calculate the total energy that prevents this collapse. So this is what we get. So these are the regions, the bluish regions are the regions that the gravity is strong enough to make that region to collapse. But all the individual regions, they were plotted in these maps. Here where I show 3 regions, A, B, and C, where A are unbound regions, B and C are bound regions. But C is the only one that contains the regions where you expect the collapse to occur because the mass is larger than the gene's mass. People usually consider B and C as the total collapsing regions. That's why they get 50 or 60% of star forming efficiency. But C is actually what you expect to collapse and not to be destroyed by the turbulence itself. This is the PDF of the cores that we get. There is a time independence of the PDF. As the time goes on, the PDF gets less log normal. This is for subsonic case where we see no collapse, and this is for subalphenic where the magnetic field is strong. So you see that the magnetic field is doing nothing actually for the collapse of the clouds. My time is running out, so I will show the last 2 plots. So this is the star formation rate obtained for the 6 simulations. The error bars are related to an average and the dispersion of the values obtained for as the time of the simulation goes on from 1 dynamical time to 1.5 dynamical time. And on the right, I see the star formation efficiency, where you see that the star formation efficiency and the star formation rate increases with the sonic Mach number, but it slightly depends, or basically statistically is irrelevant, the correlation between these two parameters with the level of magnetization of the turbulence. And this is quite surprising, because usually people believe that the magnetic fields are responsible for sustaining the collapse. But there is a reason for this. As the shocks enhance the density, since the Alfvén speed depends on the density, as the density goes up, the Mach number also goes up. And most of the cores are super-Alfvénic, even though the whole cloud as a whole, in the 10 parsec wide simulation here, they are sub-Alfvénic. The cores themselves, they are super-Alfvénic. And this is what's important, because the turbulence within these cores, they will be super-Alfvénic. And as we know, due to reconnection, magnetic reconnection, for instance, most of the magnetic energy will be removed, and also waves can be used to remove part of the magnetic flux. This is observed, actually, but nobody has connected these two informations. Data from Zeeman measurements, as shown by Crutcher, and polarization measurements, of course, from, this is a review, Pato and Fissel, they show that there is a break around 10 to 2 to 10 to 3 particles per cubic centimeter, and this is more or less the scale at which we also see the collapse of this core. So this is around 0.1 parsec. So these objects, they become super-Alfvénic, even though at large scale they are not. So these are my conclusions. Sorry for the time.
Thank you, Diego. So I suggest one quick question before the coffee break. Okay. At the back.
Hi. Just a curiosity, how do you model the viscosity of the cloud and so the dissipation scale of the turbulence?
Okay. We have explicit viscosity. The viscosity is determined by the resolutions, not determined by the resolution, but it changes as the resolution changes as well, because we don't want to keep the numerical viscosity to dominate. So we have the explicit viscosity, but we play with it to keep it as small as possible. So in the 2048, for instance, in the code unit, it will be 10 to minus 5, roundish. Also with the resistivity, because we don't want the numerical errors to dominate the diffusion.
I propose that you ask any other question over the coffee. So let's thank Diego again, and let's reconvene. Please, let's reconvene at 4:10. Thank you.